Okay, so the first thing we're gonna do is we're gonna determine which dimensions are gonna be our according axis. So for my x-axis, this is gonna be my x-axis, so D1, and then my y-axis is going to be D3. So this is y-axis, and then D2, so the height is going to be my z-axis. So this is how I'm going to set up my coordinate system, and this point is going to be my origin. So now I'm not going to think about the numbers as much because I don't have a calculator near me, but I'm instead going to explain how you should think about this problem. So if we look at the two easy axis first, so let's look at the y and z axis. So let's look at the z axis first. So first thing first, I'm gonna assign a color to each of these things. So iron is gonna be red and aluminum is gonna be blue. So if we look at the z-axis, what we're really looking at is this point of reference. So I'm going to color it out. So this is the iron and this is the aluminium. And then we're going to analyze how exactly we are going to partition it so that the mass is evenly distributed. So since the z-axis is like down here, the partition that we're going to do, which are dz, are going to be this way, like this, so forth. So every single partition of the mass is going to look like that. But so where exactly do we part so that it's even? So if we look at that, it's pretty clear that exactly in the center is going to be where the mass is even. So that's it. Like, that's how you figure out z-axis. So this is z-axis. And then using the same logic, if we look at the y-axis, so dy, we're going to once again draw colors. So for the y-axis, it's you're looking at the top view. So here you go. This is the y-axis. And then, so we're looking at like this view, and the y-axis is down here. So dy is going to be parted like this, right? It's going to be parted like this. It's going to be parted like this way. So it's the same logic. By symmetry, this point is going to be where the number is going to be parted exactly equal, which is why it's D3 divided by 2 for the number. So the hardest part is analyzing the x-axis, because this is where you actually have to do some math. So for the x-axis, I'm still going to look at it from the top view, but we're parting it in a different way because, okay, I'm going to draw the thing again. So this is the top view still, but this time our axis is like this way. So this is x-axis. Therefore, so our partitions are going to look like this. But now we know that the iron is much heavier than the aluminum, which is blue. So we know that the COM is going to be towards the iron side, like somewhere here, but we don't exactly know where, because for any heavier object, there's going to be less distance needed to like do it. Like, just think about it. If this is lighter and this is heavier, to distribute the mass evenly, you're going to use less of the heavier mass and like put some of the heavier mass for the lighter object so that the total mass is distributed evenly. So how you would find that, like find this actual value, is you would first find the mass of each of these objects using m equals dv, so density times volume. So densities are given for each of them, and for volume it's just length, width, height. And then once you figure that out, and then you want to label their center of masses, their x-coordinate. So since the two objects have equal mass distribution, their center of masses are just going to be exactly like halfway throughout this dimension. So their center of mass is going to go through here and go through here. And then you're going to use the equation, which is 1 over m integral r dm. But what this really means is you're going to do, so the first mass, so mass of iron times the x-coordinate of iron center of mass plus mass of aluminium plus x-coordinate of aluminium, and then over the total mass, which is mass of iron plus mass of aluminium, and then that will give you the XCOM. So yeah, that's it for this video.